Okay. Good morning, everyone, and welcome to the Applied Networking Research Workshops 2025. So I'm Anna Brunström from Karlstad University, and next to me is Ryan Beckett from Microsoft Research. And we have the pleasure of sharing the ANRW workshop this year. So great to see you all here this morning. We have a quite exciting program to look forward to, I think, with lots of interesting talks and also a poster session, as we will see. But before we start, some of the formalia. So the ANRW is not part of IETF, so the general IRTF intellectual property rights do not apply to the workshop. But we still follow many of the things from the IRTF, so we will have recordings of the meetings. So unless you have put on some do not photography bad lanyard, then you will be in the agreeing to be in these recordings. And we have some special arrangements possibly for one of the talks. And if you participate online, then turn on your camera and microphone when it's your turn. We also have followed the regular privacy and code of conduct. So we follow the privacy policy of the IRTF. And of course, we hope to have a nice discussion and a very good atmosphere during the workshop and the discussions between the participants. And if you need further information, you can look at the code of conduct and the anti-harassment procedures.
So just a few quick statistics on the program this year. So we had two kinds of papers. We had regular papers and short paper submissions. And we received 55 paper submissions this year, which was quite a bit higher than in some of the previous years. And we accepted around 28 papers, which was in line with prior years. But what this means is that it's a very packed program. So we're going to try to move through everything very efficiently. We have 15 minutes scheduled for all of the regular papers, and that includes all of the Q&A. And, again, the load was quite a bit higher than we had anticipated. So thank you to the program committee and everyone who did a great job getting their reviews in on time and with a lot of great feedback. So thanks to all of the program committee and all of the support staff who helped us from IRTF and ACM. In terms of logistics, so a quick couple of things. So the program and the PDFs are going to be made available through the ACM digital library, and they should be available sometime today. And you should access them, if you access them through the IRTF link that we've pasted here, you should get open access to those PDFs. And then the meeting link and slides you can find on the data tracker, and sign into the session with Meetecho. And if you have a question, try to remember to join the queue, and we'll call on you, and then you can ask a question. So here's the schedule we have. So we're going to start with the keynote speaker from Laurent, and then we have a quick session with two papers on video and CDN. We'll take a short break, and then we have two more sessions on standards, protocols, RFCs, and then emulation and diagnosis. Then we'll break for lunch. And when we come back, we have three more sessions plus a lightning and poster session. So we'll have transport, a 45-minute lightning round with 7 one-minute talks, and then followed by posters, and then a routing session and a security session. And so with that, I can hand it over to the keynote speaker, Laurent. So just a few words on Laurent. So Laurent van Bever is an associate professor at ETH Zurich. He leads the network systems group there, and he works on making large network infrastructure more manageable, scalable, and secure. He's received more awards than I can count, including the SIGCOMM Rising Star Award, multiple SIGCOMM Best Paper Awards, NSTI Community Award, 6 IETF, IRTF Applied Networking Research Prizes, an ERC Starting Grant, and so on. And in June 2024, Laurent co-founded netfabric.ai, a startup focused on smart network observability, where he serves as the chief scientist. And he completed his PhD under Professor Olivier Bonaventure at the University of Louvain. And he was a postdoc at Princeton under Jen Rexford, where we overlapped for a couple of years. So he's going to tell us about tackling some of the problems with misconfiguring networks. And please take it away. Yeah.
Thanks. I would like to start with a picture. So please take a moment to observe this picture of the part of the European airspace. We're in June 2022. And there is something weird in this picture. So just try to look at it. And as a hint, I happen to work and live in Switzerland. So let me overlay Switzerland on that thing. And as you can see, there are absolutely no planes flying over Switzerland in that morning. It's a beautiful morning, very sunny, absolutely no problem there, which is highly unusual. What won't be unusual for this crowd is that the reason why this thing is not happening is that the entire Swiss airspace was closed due to a network outage. So the outage affected SkyGuide, which is the company that essentially oversees the Swiss airspace, and it was a network outage that took down their infrastructure, and so they had no choice but to close the entire airspace for about 2 hours. So the outage lasted 2 hours, but the closure lasted for 5. And of course, wreaking havoc in all kinds of ways, as you can imagine, on that day. So the cause of that problem was a hardware failure, at least according to the post-mortem. And this is far from being an isolated event. So network meltdowns, as we call them, happen really all the time. So another very famous example happened just 1 year before. It was the Facebook case, where the entire infrastructure of Facebook went down also for a couple of hours. So Facebook, Instagram, WhatsApp, all these platforms went down. This time it was for longer, it was for 7 hours. And it was so bad that the people could not enter the data centers anymore because the locks were connected to the network, of course. And so that's part of the reason it took so long, allegedly, is that people had to find the physical keys to enter the data center to reboot things. So I think this crowd knows very well that networks are still in 25 quite easy to break and quite hard to repair. At least it takes a long time to repair this network. And so how come? How come it is still so easy and so hard to repair networks? So I think one of the problem is, of course, the problem of configuration. So configuring a network is hard today, very hard today, because of a fundamental semantic gap. So if you take a high-level view of what the network is doing, what is sitting at the core of a network, we have distributed routing algorithms, OSPF, BGP, ISIS. These routing algorithms, what they do is that they compute forwarding state. This forwarding state is then downloaded into the line cards, into the data plane of your network, and drives the traffic inside the network. So these algorithms, they compute this forwarding state, and what they take as input are devices configuration, the topology that they track, like what links are up or down, and then any external routes, for instance, BGP routes. And so the operator in this picture appears at the top. What the operators, what they have in mind is essentially they have high-level requirements about the forwarding behavior of the network. So they want, for instance, the traffic between Madrid and Barcelona to take specific path, perhaps to be load balanced on at least 5 paths. And they want, I don't know, like the network to converge always within a second after any possible failure. So there's these very high-level requirements. And so from these high-level requirements, what they need to do is translate them into low-level configurations. So these low-level configurations, they can be huge, like hundreds of thousands of lines, and times like the number of routers that you may have. So you might end up with millions of lines of configurations, and any one which is wrong could potentially take your network down. So there is really like there a huge semantic gap that right now operators mostly have to fill manually with their brain. And so it shouldn't be a surprise that it's, of course, easy to shoot yourself in the foot, and that the majority of the downtimes are actually ultimately attributed to human factors, human errors, more specifically. So network verification here is kind of like a godsend, right? So it really promises to significantly improve the reliability of network infrastructure. And so in case you do not know about verification, what you have in verification is that you get a specification, typically a formula that describes what the network should do. And you also have a configuration. And then the problem of verification is to kind of like ensure formally prove with math that your configuration is compliant with the specification. And then if it isn't, then it will give you a counterexample, a concrete scenario where your network is wrong. And you as an operator, you can then look at this scenario and then try to figure out, okay, how you should change the configuration accordingly. That's kind of like the verification task. Same thing in software verification. Instead of like verifying a config, you verify a program. Same problem. Network verification has been widely successful. First, of course, in academia, where kind of like I'm from. So there have been countless papers on network verification for the last decade or so. So I only list 5 here, but believe me, there are way more than this. But also commercially. So some of these papers, at least 3 here, they went on to become startups, and then some of these startups also went on to become acquired. So Veriflow was acquired by VMware, and then IntentionNet was a few years ago acquired by Amazon. So clearly there is also like commercial interest, of course, in making network more reliable. So yet, still in 25, if you open the news and look for network meltdowns, you will find many hits. So still in 25, networks do go down because of misconfiguration. So it's still not gone, far from it. So that either means that network operators, they actually are using verification, but they just either do it wrong, or verification happens not to be enough, or they simply do not use verification, and there they could do that either voluntarily or not. And wherever we stand here, the question is really why and what is missing, right? So why don't we see like perhaps network verification being more widely used? So I think it's a complex question, and there are many dimensions there. What I would like to kind of like unpack in this talk is kind of like 3 dimensions that I think explain this. So the first one is that verification itself, or like the existing verifiers, they check a very restricted set of properties. Granted, these properties are very important for operators, but operators, they also care about other types of properties that, if violated, could take down the network, and these verifiers do not verify those. So that could be one explanation why we still see meltdowns. Another thing is that verifiers, they can be imprecise. They can under or over approximate network behaviors. That means they can essentially tell you sometimes that the network is correct while it isn't, or they can tell you that the network is incorrect while it is. So false positive, false negatives, that can happen with verification tools. And finally, I don't know how many of you have used verifiers in the past, but they're not really user-friendly in many cases. So it's still a problem for most formal methods. It's hard to use formal methods in practice. So that's also an issue. So in my group, I've been working on these problems, trying to make verification more practical for a couple of years now. And what I would like to do in the rest of this talk is essentially show you a couple of our results there, trying to increase the number of properties that verifier supports, trying to increase their coverage, and also trying to increase their usability. So I would like just to kind of like show you recent papers in the last 5 years that kind of like fit in these categories. And then after, I would like to take a step back and then also talk about perhaps a broader picture about operations, and also try to see or try to discuss with you whether AI has some place in that. So properties first, more properties first. So I told you, like, existing verifiers, they check a restricted set of properties. So what I mean by this is that most of them actually typically verify forwarding level properties. So essentially they verify properties that pertain to the content of the forwarding table of your network, like the forwarding entries. So they can check things like what is the path taken between A and B, whether A and B can discuss with one another, whether they are isolated or not, whether there is load balancing, that kind of things. So that they can do. But for instance, they cannot reason about the traffic that goes over this path. They can reason about just the path itself. And another thing that verifiers, they do, just for simplifying the problem, is that they reason about these properties in the steady state. So that means that they will reason about these properties once the network has converged. And they assume that the network will converge. And so being in the IETF, I guess you also know that in theory, at least, networks are not guaranteed to converge. So you can have oscillations problem. So that means that verifiers, they won't tell you anything about these properties as the network is converging, for instance, after a failure. So depending on the criticality of your requirements, you might also care about this, of course. So as I said, operators, they care about other types of properties. Traffic is typically like one of them. So they care about, for instance, congestion in their network. But they also care about how long properties are violated and how often. So most of the operators, they have SLAs, so service level agreements, 4 nines, 5 nines. And what they need to ensure amongst the customers is that they are like, indeed, like, I don't know, having a level of reachability which is above 99.999%, for instance. So that means it's okay for the network to be unreachable sometimes. So they don't necessarily care that the verifier will return them an example where the network can be unreachable. What they care about is how often does that happen and how long does that last. And so existing verifiers, they struggle to actually provide these answers as well. So as I said, I would like to now start discussing a couple of works that we have in this space. So the first one, it's a very recent one. We just published it this year at an SDI. And this is a paper in which we look at computing the maximum link load in a network, which is something that many operators care about, right? In capacity planning, you would like to understand what is the maximum load that this link can take, because you might, for instance, have to upgrade that link accordingly. And so if you think about what drives the link load in a network, well, there are a couple of dimensions, a couple of factors. One is, of course, the traffic itself that enters your network. So traffic enters in one location, exits in another location. So the traffic matrix, of course, has a knockout effect about the load of each of your links. So that's one thing. A second thing are failures. So whenever there are link or node failures, of course, in your network, protocols will converge, and they will put this traffic on a restricted set of links. So that will increase their load. And so you might, again, as an operator, be willing to have no congestion, for instance, under any single link or node failure. And then finally, what also will change the load in your network are external route advertisements. So if you think about an ISP, for instance, and the Netflix prefix, if the egress point of Netflix changes at peak time, this will have a knockout effect on the load in their network as well. So it turns out that existing tools there, they kind of like that can reason about worst case link load. They only consider failures and the traffic matrix. They kind of like completely disregard or don't consider like BGP routing inputs. They consider them as fixed, which is a big problem. So this is like a plot that shows the extra link load that each link in the medium-sized ISPs can see after failures, up to 2 failures link. So you can see that here, the median case, so 50% of the link can see up to 20% extra load when you consider failures. So you might think as an ISP, well, that's pretty okay. I mean, 20% I can handle, no problem. The issue, though, is that if you add on top BGP route changes, and you consider up to 10 of them, then the picture changes. Now, as you can see, like the median load across your links can increase by up to 70%. And at this point, then it might be above the threshold that you might be comfortable with as an ISP. So meaning really like you need to consider route changes as well. Just link failure doesn't cut it. So the problem, of course, is that there is a reason why existing systems don't look at route changes is because it's already hard just to look at failures. And so navigating the joint space of failures and external route changes is huge. So it's huge because a BGP destination can be, in theory, advertised by any subset of your neighbors. So if you have 30 neighbors, you already end up with a billion subset that you have to consider. And 30 is not big for many ISPs. Of course, failures that can affect many destinations at once. So that create dependencies between all these prefixes. So you cannot easily separate them and deal with them in parallel. That doesn't work. And as you know, being at the ANRW, the BGP routing table today is above 1 million prefixes, V4, V6 combined. So this is a huge space, and so this is, of course, challenging to navigate. So I won't have the time to go into the details. If you want, we can discuss about that, but also you can check the paper. But just to give you like just the intuition, we use two insights in the paper. The first one is that we show we can shrink the search space without losing accuracy. So that's kind of like nice reasons. And then the second thing that we do is that we shrink the traffic matrix, the input. And there we lose accuracy, but we show how we can do that in a controlled manner. So you can tell me how much precision you are like, you agree to lose, and then we can shrink the traffic matrix accordingly and still be within the bounds, probably. So doing these two things actually work quite well. So we have been able to analyze ISPs of reasonably, let's say, sized ISPs with up to 2K links in a couple of hours. And you don't need to do that analysis every 5 minutes, okay? So this is more like a design task that you could run even like every day, but like 3 hours to essentially analyze an ISP is pretty reasonable, we think. So that was the first work. So here we are extending again like verifiers so that they can start reason about traffic. In this work, it's a bit different. Now we want to make verifiers able to reason about uncertainty and probabilities. So we want essentially to verify SLAs type of contract. So we like to verify, for instance, the probability of reachability being higher than 99.99%, for instance. So one problem that you have there that verifiers do not have is that a verifier, it either gives you one counterexample or it tells you that there isn't any. If you want to compute a probability, that means you need to list all of the counterexamples and count how many they are with respect to the entire universe of scenarios. So you need essentially to kind of like enumerate the space. And you need to do that with an accuracy which is high enough to be able to verify 4 or 5 nines SLA. Otherwise, it's kind of like useless. So that means we again have a search problems. We have many search problems in my group. And solving these search problems, again, like is hard to scale. So if you do it naively, you might quickly end up with millions of scenarios to consider. Just as a kind of like intuition here, just computing one scenario takes about 12 seconds with a verifier. So if you multiply this by millions, you of course end up with something which is untractable. So in this paper with our system NetDice, we show that you can actually do this by considering only a few thousand of these scenarios. So we managed to kind of like shrink the search space a lot. And the intuition, I would just give you it briefly, is that we kind of like prune the search space massively. And we do that by kind of like reasoning about what failures can really affect what properties. So here I will give you a trivial example where you have like a very simplistic network. All the links are 1 in weight except 1 which is a cost of 2. And we're looking at the traffic between A and B in this case. So the operator cares about the probability that this pass will be taken, okay? That the green pass is followed. So I guess it's pretty easy to see that if you have a failures of 1 of the 2 green link, of course that will affect the pass, right? The network will converge around that. But it should also be clear to see that if you have a failure of any link which is not alongside the shortest pass, then routers will not move the traffic between the A and B. It will still flow alongside the pass, which is the green one. So essentially, what it means is that given a property and given the failure scenario, then some of the failure scenarios are irrelevant. They don't affect the probability of that property being true. So we call these cold edges. Okay, and so it's trivial to find these cold edges in the case of shortest pass routing. You can really easily do an algorithm for that. It's much harder to do that in the case of BGP, for instance, because BGP is policy-based. So you can have actually pretty intricate logic, which is followed by the router in order to pick a path. So in the paper, we actually show that that's the main reasons, but I just wanted to give you the insight for shortest path as well. So we do that for BGP, as I said, like supporting also things like route reflection, considering partitioning and dependencies on IGP as well. So the good news there is that when you do this, so you can massively shrink the search space, and then we end up being able to, again, analyze reasonably sized ISPs in minutes, okay? So it will still be challenging for us to analyze, I don't know, a Deutsche Telekom or an AT&T, but like reasonably sized ISPs we can do in minutes. The last paper I would like to mention before closing that first chapter is reasoning about time now. Okay, so this is a paper that we haven't presented yet. It's going to be presented in December at CONNEXT, and this is a paper that tries to reason about how long in seconds can a property be wrong. Okay, so as I told you initially, verifiers, they can verify properties once the network has converged. So that means that as the network converges, all bets are off. Okay, your beautiful property like traffic should never bypass my firewall can be off for 30 seconds if the network converges during 30 seconds. Okay, so for me that was always an issue. Okay, I know that networks, of course, they see failures all the time, and so they converge all the time. Also, they see external routes all the time. Okay, and so it's for me a big problem that we cannot really reason about how wrong we can be in these cases. And so there is kind of like a research question that we try to address in this paper is how long can these transient violations be and how often do they appear? That's kind of like the problem. So again, it's hard to do that. Why is it hard? Well, routing events, they can affect any and many prefixes. And violations can actually be very short-lived, so milliseconds. But what you want to do is to kind of like consider integral, like the sum of all the violations, because that's what the operators care about. So if you have like 20 milliseconds violations very often, that can sum up to a lot of traffic being lost. So you also care about this. But when you put these two things together, what it means is that you cannot probe for this. You cannot actively probe all the destination, all the million-plus destination that you have in your network aggressively, like at the millisecond granularity, in order to catch this. You cannot measure this directly with probing. So what we do in this paper is that we kind of like go at it from a different angle. What we observe is that many operators, they collect logs, control plane logs. So for instance, like about the BGP events or like the RIB events, the routing table events or FIB writes. And so the question was, can we try to infer what is going on in the data plane from essentially control plane logs? So we have the timestamp of a BGP route arriving, a withdraw arriving on the router. Can we try to guesstimate what is the timestamp of the corresponding write to the FIB? And from there, kind of like estimate what will be the traffic effect. That's kind of like the problem that we had to deal with. And so there, again, like we had a challenge of like bridging a gap. So there are a lot of things that happen in between a BGP router receiving a prefix and then a write being actually activated in the FIB of a device. Okay, so we have to kind of like bridge this gap and kind of like model what is the control plane doing. The good news for us, and again, I have to be brief here, but that we showed that you don't need to model the entire control plane, thankfully, because that would not have been possible. But as previous research has shown from my advisor, who is perhaps in the room, like the main bottleneck in convergence tend to be the RIB to FIB link. So the link between the control plane and the data plane, this pipe that you have tends to be bottlenecking convergence time. And so what we showed is that if we model just this bottleneck, we can actually kind of like build a model which is crude, but good enough to actually give us accuracy which is below 25 milliseconds on average. So we can, with this system, we can estimate violation time for any prefix with an accuracy of around 25 milliseconds on average, which is, we think, good enough, again, like for practical usage by operators. All right, so we have been talking about properties, how we can increase the kind of like number of properties that verifiers support, reasoning about traffic, probabilities, and time. What I would like now to kind of like switch gear a little bit and talk about coverage and precision. So as an operator, you should only trust the verifier blindly if it is sound and complete, okay? So just in case you do not know, so sound means that a verifier will report all bugs, okay? And complete means that the verifier will report only bugs, okay? So it's kind of like false positive, false negatives again. So ideally, you need really both. You need soundness and completeness, okay? And if you have both, then you can really go for it, and you can deploy the correct configuration without any issue. The problem is that ensuring both is actually impossible. So there have been like very famous theoretical results that shows for non-trivial problem, and network verification is definitely non-trivial. So it's the Rice theorem. It's impossible to have both soundness and completeness. So that means most verifiers, they have to let go of one of the property, and typically they let go completeness, but they still are sound. So they will not tell you that something they will not miss bugs. So, but they might give you false alerts. They might tell you that a configuration is wrong while it isn't. That's kind of, at least that's the goal that they should have. Why is it non-trivial for verifiers? Well, because, I mean, you are at the IETF, you know how messy protocols are, so that's one thing. There are many of them. There are countless extensions that are always discussed at the IETF. So you need to model them all, okay, perfectly. And you need to model them all, not only the spec, which is in the RFC, but you have also to model all the differences across the vendors, the devices, and the OSs. And if you miss any of those, right, your verifier and your network might start to kind of like essentially not agree with one another. And so that means that the results of verification might not be useful for you anymore. Plus, and that's the worst thing, you have also to be able to model any possible bugs that, I don't know, Cisco, Juniper, Brocade, Arista have, because these bugs will affect also the router behavior, and they might make the router go left while your verifier thinks that according to RFC, you should really go right. But if your traffic is really going left, okay, then as an operator, that's an information you need to know, because that's essentially what your customers also are observing. So it's not a problem which is only for network verification. It's also a problem for software verifiers. And there is this nice quote from Donald Knuth, who is emeritus now professor at Stanford, who is the author of The Art of Computer Programming. I guess some of you know this sequence of books. And so he said, like, this very nice quote: "Beware of the bugs in the above code. I only have proved it correct. I've not tried it." I think it really really rings true for network verification as well. So you need to be careful even when the verifier tells you it's correct. So here I would like to more quickly now kind of like talk about two works. The first one is how we can detect problems in verifiers, or how we can verify the verifiers, if you wish. And then the second one is how we can actually avoid having to build the models that the verifier used manually, because I mean, I have my PhD student, one of my former PhD students in the room. You can ask him. It takes months to actually build a model that the verifiers use. Months of work, full time. So it's really, really hard. So if we can automate this, then perhaps there is a hope that we can actually try to keep up with all the new features and all the new bugs that control planes will exhibit. And we'd like to do this ideally automatically. So the first paper is, again, like an NSGI paper, 21, Meta. So there it was all about testing verifiers. So what we do in Meta is that we essentially generate configurations. So we have like techniques to do that. And then we give these configurations to verifiers on the left side. And then we give this configuration to a live network on the right side. And then we look at what the verifiers compute, and we look at what the actual network is computing, and any delta is an issue. That means that the verifier is not accurately capturing the behavior of the network. And so, of course, that's just the intuition. The kind of challenge that we had to that we had to do is, first we had to figure out how to generate configurations. So it's actually hard if you want to generate a gazillion of configurations, that not to generate gibberish, okay? So if you think about configurations, network configuration, there is a lot of structure in them, okay? There are dependencies. If you configure a BGP session on A, you need the corresponding parameters on B, otherwise the sessions won't go up, and then you won't test anything about BGP, for instance. So you need to capture this logic somehow, and yet you also want to have randomness on top so that you can actually generate random configuration on top. So we solved that using kind of like fuzzing techniques, so testing techniques from software verification. And then you also want to have some kind of like idea about how well you are covering the space of configs, how well you are covering the features in that world. So we also have techniques that come from verification that kind of like give us a way to reason about how many features we are covering and how well we are covering these features. And then if I give you a config which has, I don't know, 50 lines of code, and that config computes a different outcome than the real network will compute, it's very hard for you to figure out where is the bug in the 50 features that this configuration has. So we have techniques to kind of like zero in on what features is the problematic one once we found the problem. So that's kind of like the third aspect there. So we fully implemented Meta. It's open source. You can use it. It's online, and it supports protocols like OSPF and BGPs, policies, etc. And then we, of course, use it to test actual verifiers. So we tested 3 of them: Batfish, NV, and CBGP, and we indeed found bugs in all of them. And so these bugs were, I mean, one issue is that a lot of them were kind of like silent bugs. So that means that they affected the soundness of the verifiers. So that means that there were bugs where the verifiers was not saying that there was a problem in your network. Okay. So this, of course, is an issue when you are an operator and you want to ensure correctness. All right. So now, how can we avoid building these models accurately? So this is the first mention of AI in my entire talk. But what we wanted to do here is to see whether we can actually avoid having humans writing these models. Because again, like, it's great to have these models, but humans will not be able to scale with the amount of protocols and features that we have. And so here I will be very brief. It's a paper we had in 22, but essentially that's the question: can we learn how to configure a network? And the answer is yes, but there is a big gotcha. But essentially what we did is that we trained a neural network, a graph-based neural network, to essentially invert network computations. So we essentially trained a neural network to kind of like compute what BGP, OSPF, RSVP, LDP, etc. are computing. And we did that by, it's very easy to generate data to train these models. You generate pairs of configs and also the specification that this configuration has. And then you feed that into the neural network, and then you let them train. So this is fully automatic. So it works to an extent, as I said. So it's clearly not perfect. It's not yet production ready, but it shows good promises. So what we observe is that these tools, they can actually compute. I mean, they have an accuracy of around 90%. So that means if you give me 100 specification to meet, these tools that are completely trained, so no humans involved, they can at least produce configuration that will satisfy up to 92 of them. So, which is not bad, I think. But of course, the question is still the remaining 8, okay? That then you would need, at least as of today, to fill in with human knowledge. One thing I would like to mention as well is that it's much faster to run these tools than to actually run verifiers. So once you have trained a neural network, like running it forward, the inference time, we are talking about milliseconds. So these things are 500 times faster, actually, than existing verifiers that are relying on things like SAT solving, which is very heavy in terms of computation. So it's promising, shows promises, but of course, not perfect yet. And then I would like just to, not to start speaking about usability, also a bit more quickly. But what we would like to do here is to kind of like increase the level of automation when it comes to using formal methods in networks. And here, essentially, I would like to mention quickly 2 things. So what we have done in my group is a lot of work trying to simplify the before you can use verification. So try to lower the bar to access verification, and then also to simplify the after the verification. So it's beautiful to have your configuration being verified, even assuming it is correct, really. But then you need to deploy it inside the network. And if you have like 50 routers that you have to touch and update the configuration for, you still need to do that correctly. And you can still absolutely mess up your configuration as you are changing it, okay? So verification is really just a small part in the process over there. So for simplifying the before, though, one issue, and this is a paper we published in 2020, one issue with verifiers is that you have to give the spec. So go ask a network operator working for Deutsche Telekom, what is the specification of the DT network? I mean, I would be ready to bet that they have no clue about it. No. All right, okay, so we can discuss. But also, even if they had clue about it, it would be very hard for them to actually write it down, okay? Because we're talking about, I mean, for most of them, logical formulas capturing the logic of the network. And so we actually did a small experiments here looking at a very small network, so not DT, 10 routers only, and we ended up with thousands of policy predicates. So that means the formula that you will have to write has thousands of predicates. And there, of course, you can get it wrong. And if you get the spec wrong, then anything is wrong after that, okay? So we thought that is a big problem. So DT might not have the spec, but DT has a running configuration, okay? So there is a configuration running in DT, and if we expect that the network is more or less correct, what we can do is extract the spec from the running network, and then we can at least start from there. So that was the observation we had, is that if we can learn the specification from the running network, then we can use that and then detect, for instance, deviations from the specification as we move forward, and we can at least explain the differences in the behavior from one configuration to the next. So that was the goal in config to spec. And so there is actually a very nice way to do that, and I don't have the time to explain, but would be happy to explain it offline. The last thing I would like to mention as a work is the deployment case. So how do you reconfigure a network, a running network, without again shooting yourself in the foot? So it's kind of like an open heart surgery, right? Your network is always running, and you need to touch it, you need to modify it without killing it, so that you can just reconfigure it, okay? So this is a problem. So network configuration, the formal problem is the following one. You get a spec, again, you get an initial and a final configuration, and then you have to figure out a sequence of intermediate configurations that you will apply to your network such that all of them are compliant with the spec. So this is definitely not a new problem. This was actually the very topic of my PhD thesis, and I graduated more than 10 years ago now. But the issue, and the issue also in my work, in my thesis, is that it's the overhead that existing reconfiguration techniques had so far. So these techniques, they either require you to duplicate everything, duplicate the entire control plane, all the routes, double them, or they temporarily freeze the control plane during the reconfiguration. And both of them are not acceptable when you talk to operators, and they tend to dismiss the techniques altogether. So in that last paper, Chameleon, we kind of like developed a system that can reconfigure networks in place, so without duplicating anything, one router at a time, and it can do so correctly, and also within 5 minutes, even for large networks. So we think it's kind of like a good kind of like closing to this problem. So I'm done with the main part. So what I've talked about is how we can bring more properties in verifiers so we can increase the coverage and increase their usability. And just as a conclusion now, I think, of course, I mean, we are the IETF, so I expect even a question on this, is that configuring a network is just a small part of operations, okay? So as a network operator, you also have to design, monitor, optimize, secure, troubleshoot, etc. Okay? And so there are many, many other tasks as well than go beyond just configuration. And so similarly, I think, to configuration, many of these tasks today are still bottlenecked by just us human not having enough cycles to actually do them all. Okay, so human reasoning is still a bottleneck in many of those. And so similarly to configuring, you could try to approach all of these problems in a model-based way, and many people do that, or in a model-less way. And also many people try to do that nowadays with data-driven techniques and AI. And I think if you compare these two things, model-based and model-less, alongside guarantees, coverage, explainability, and overhead, both of them are very actually useful. So model-based, so again, like what I've presented today, you get very strong guarantees on a reduced coverage, only on what the model can support and where the model is correct. It gives you absolutely high explainability. I mean, the model can explain what it's doing, and so you know why the model is telling you that it's correct or incorrect. The overhead, though, is high because you have to build the model in the first place. So it's an upstream overhead. You have to spend a lot of time crafting the model and updating it. In a model-less way, data-driven way, the guarantees are, well, few, if not none. Coverage, though, is high. At least these models, technically, they can handle anything, okay? Expandability is very poor, so it's black box, okay? And the overhead is high, but downstream, because you really need essentially to be mindful of their pitfalls, and you have essentially to cover for them. So of course, like what I'm interested now is to try to combine these two things together, because both of them are, I think, complementary. And so what we are thinking now in our research is how can we combine model-based, where it shines, with model-less, where it shines as well, and try to get the best of both worlds. And so we have like a poster at SICOM coming up, where we try, for instance, to benchmark really precisely how good LLMs are at network operations, if you are interested. They are not great, but they're not bad either. That's the Cliff Notes. And there are probably ways to make them much better. And then also, I mean, as was mentioned initially, we also have a startup now where we try to also bring some of our research to the real world. And so what we are doing with NetFabric is trying to kind of like combine model-based and model-less for network observability. So it's more like the problem of like reasoning about network behaviors from measured network data and kind of like try to bring you insights out of that. So if you are an operator and you are interested, I would be happy to chat. With this, I'm done. So in the next part of my research, I would like now to focus on this little thing, which is essentially, I think, why many of these networks still go down. And I would be happy to take your questions. Thanks.
Okay, we have a question from Sergey.
Thank you, Laurent, for very nice overview of your work. Actually, I want to go back to your motivation when you talk about Swiss ASP outage 3 years ago. So here in Spain, there was a big sensation in April when we had a great blackout. And in addition to power grid, networking was not very useful. So do you see any role for network verification in this type of settings, basically interaction between power grids and computer networks, cascading failures, and what network verification can do with this?
I think, well, I was fearing you will ask me, how can we verify that the grid is correct? And that I think network verification cannot do much there, but like the electrical engineers, I think are working on it. That said, I think regarding using verifiers to reason about power cut, I think this is totally doable. So I think power cuts, they manifest themselves as failure scenarios. And of course, you have all these dependencies because of the grid, you know, like, but you can definitely model that as a failure in your network. And you can reason about where the UPSs are, for instance. You can reason about how long they will last before they really go down. And that, I think, can be definitely incorporated into a model. And then you can reason, for instance, about like properties like reachability against these kind of failure scenarios. That would need that, of course, you will need to kind of like be able to know, how is the power infrastructure kind of like connected, let's say, to my network, and where are the dependencies there. So if you can get that kind of input, I think you can absolutely use existing techniques even. So I think probably many people are thinking about it now, right? After the last crash, it would make sense that people are thinking of it. Yeah.
Yeah, because there are some kind of understood things you can do and you cannot do, because what happened in many places here is people were running their infrastructure as long, is it lasted for normal usage, for example. So you don't kind of rate limit or limit the activities. So there could be some intelligent strategies how to make sure that your infrastructure lasts longer until power grid is restored.
Yes, absolutely. I mean, this is something I've not talked about at all today, but we are also working on network sustainability, you know, like how can reduce the power consumption of network infrastructures. And of course, when you are into a blackout and you are running on batteries, these strategies, they make absolute sense. You know, like you probably don't care about necessarily, like video streaming that much in these moments. And so it would be totally fine to even reconfigure your network massively for like also power savings. So that absolutely, I think you're correct there. Yeah.
Thank you.
Okay, we have a question from Rudiger.
Yes, Rudiger Volk. Until 5 years ago, when I retired, backbone architect for Deutsche Telekom. Kind of, Laurent, what I wonder is what kind of trade-off are you considering, or how do you consider the relation between going, or well, okay, asking the operator for a formal formulation of what the network is supposed to do to correct configurations via, well, okay, somehow configurations happen, and then you shoot off a verifier to check whether the specifications are met, or going the other way around, the constructive way, where you try to offer languages that are close to the domain where the operator thinks and would like to specify. And, well, okay, yeah, like a high-level language compiles that into configuration. And then the verifier would be doing, well, okay, have the assembly machine language program be verified instead of the high-level language input.
Yeah, I think this is a great point. I did not mention it, but I have, a blog post on like the difficulty of specifying network today. And one of course, the strategy is indeed raising the level of abstraction of the specification language, which is extremely low level. And so I think there is research there that needs to be done in how, like, what should this language be? I don't know if that could be perhaps even something that the ATF could work on, like, can we agree on how we should specify what the network should do? And that is indeed a specification language, and that exists for like code. And that you can indeed then compile it down all the way to low-level formulas. I think this is absolutely research worthy and something to do. Yes, you're right.
Yeah. So kind of responding to your claim, DT has no clue. Well, okay, no clue is a really large claim. I know that for BGP policies and configurations, I did my specification language with compiler to multiple very different target languages. And for the traffic engineering stuff you were mentioning, kind of the essential part, or one of the essential parts of the input is the traffic matrix model that you offer as well. Okay, that should be satisfied. Yeah. And kind of tools for taking that and kind of constructing configuration, including the update process. So have been around and have been used for, I think, 20 years now.
No, it's great. And I mean, I think many operators are doing the right things, like it's just like, I don't think all operators are doing that. And so, as you said, I think the goal is to increase the number of people who can do exactly what you have done there. And I think like learning the specification out of a running network is probably very, practical for many operators, like they're happy with their network today. I learned the spec, and then I go from there, and then you can do specification less verification. So, which is also like another, I think, approach to your suggestion. But I agree, and I wish more people were doing things like you. Yeah.
Matthew.
Hey there, long time no see.
Hey, long time. Thank you. That was a lovely talk. I wondered if you could comment on what it's like to work with ISPs in Europe, and whether it's been getting easier or harder. From my point of view, feels like it's getting harder in Australia, I should say.
Yes. I think it's not getting easier. I don't know if it is getting harder. We have the chance of like collaborating a lot with our provider, the ETH provider, which is the research network in Switzerland, Switch, and so they are actually very helpful in providing us with data. But even there, you know, like it has been getting harder, for instance, to access like traffic statistics lately, and so it's hard. And I mean, of course, I've been trying to collaborate. I mean, collaborating with ISPs is something we try to do as well. But typically it tends to be on a very specific projects then, and then the scope is very confined. And yeah, I mean, for research, you would like to have access, you know, like to kind of like all the data, you know, like so that you can. So it's, I think it's definitely hard. And in a sense, what is a bit sad is that, you know, like also now having another hat is in a startup, that I see it's much easier when you're a company discussing with another company. Because then these companies have no problem like signing an NDA with another company, something that they do all the time. And somehow we have access to data now through the company that I could only dream about as an academic, you know, like, and so I think there is still a lot of work to do there, yes, in order to, you know, like facilitate that. And it's still, I think, a problem. Yes.
So the idea of working through a startup is very cool. Maybe we should try that down south.
Okay, I think we have time for one or two more questions.
Should I?
Yeah, go ahead.
Hi, Debapam from Microsoft Research. So I have two questions of curiosity. First one, like, do you have any plans to work closely with some satellite operators, LEO satellites? And the second one is like, I felt that there are many components where you could probably use AI and even LLMs. For example, you told like in a configuration, if A is there is a high chance that B would also be there, right? So that seems to be a very classic case of self-attention transformers. So do you have plans to integrate in a system these LLM and AI components along with your tools?
Yes. So to your first question, one of my students actually is passionate about space research now, and so yes, I think we are looking into it, not necessarily from a verification viewpoint, but I would be very interested in understanding from your, I mean, expert standpoint, what are the problems there in terms of like perhaps correctness. My understanding is, of course, they are using routing a mechanism, and so these, I think, similar techniques can be applied. To your second point, we are absolutely looking into this. Yes, so we are, you know, like looking at how LLMs can, yeah, indeed, like can interact with the network and detect correlations amongst network data. One thing that we are doing even in the startup is that we are using LLM to generate parsers to actually then process raw data. So these issues, when you look at logs, for instance, you get logs from all kinds of devices and you cannot parse them. And so instead of just applying blindly the LLM on the raw data, that doesn't work very well. But like using it to generate parsers that then process the data, and then, you know, like you have like at least semi-structured data to process. That has been quite successful as well. So we are trying to see, you know, where it shines and where it doesn't. And but clearly it struggles with many things like IP-based reasoning, like prefix matching, all these kind of things. It's not good at this. Like it's not good at computing arithmetic, right? So it's all about figuring out what tools you need to give it so that it can still do the task correctly or not. So that's an ongoing process. And that's also why, I mean, I didn't have the time, but this last poster is kind of like going there. So if you're interested, I can send it to you.
Yeah, very much.
Yeah.
It seems like a case of agentic system.
Yeah, exactly. It is.
Right.
Yeah,
So
absolutely.
I'd
Yes.
be happy to talk offline
Yeah,
and learn
of
more.
course.
Thank you.
Thanks.
Hey, Laurent, great talk. One comment and a question. RIP2FIB is indeed the bottleneck for the convergence for an IGP, but not necessarily for a well-designed BGP network, right? So I think you cannot just consider the RIP2FIB time as a view of your convergence time to do the maths of to compute those milliseconds. Second, the question is, what should Opsaria do at the IETF to make your life easier? Because, I mean, how do you interact with the network? We have talks at Opsaria where we ourselves no longer understand the state of the sets of models that we are, right? So for your side, playing with the data that we have here, it must be even worse. How should we change our behavior in order to make your life easier?
My life as an academic, you mean? Or my life as a...
Or net fabric.
Okay.
We can take it offline. If,
no. I can try to quickly answer it. I think I think having ways to describe. I mean, I know about Yang, netconf, and all this kind of like data representation language, but so having them more widely used, you know, like I think would definitely make our life easier. You know, like a big challenge we have, and I think many people have, is just like reasoning about the diversity of the data. I mean, you have configs, you have like NetFlow, you have IPFix, you have like SNMP data, you have logs. It's all very multimodal, you know, like how to bridge the gaps between these modalities into one, you know, model that can reason about all of that together. I think this is really like the golden, you know, nugget, right? And so if one could do that, could think about them. I mean, I know that there have been attempts to try to go to these models, and I don't think they were very successful. They are slow and perhaps bound to be slow, right? So that's why like we try to go at it. I mean, this is where I think AI could help, because you can observe correlations between things, you know, like, and you know, like the fact that you could have a model that tells you, for instance, that, I don't know, like the network is wrong because of that configuration line, but you can also have AI that tells you, you know, like, I don't know whether it's that configuration line, but you changed this device configuration 5 minutes ago, and that correlates very highly with the fact that it should be, you know, like the root cause. So this is kind of like where we are going at it, instead of the model-based way. To be honest, and I've not thought of it, but the IETF being more process-based, you know, like, or perhaps it's more about the modeling, you know, like the model-less aspect. Can we kind of like reason about how to, what should be the model to train to actually reason about network data? Perhaps that could be something that the ops area could be interested in. I think discussing more between academics and ops should be, yes.
Yeah, I think they kind of agree with you, are trying. You should send your student to NMOP and to, in the future, Onion, so that they help us.
Yeah, most of them are graduating soon, so they would probably be looking for jobs anyway. Yes.
Okay, last question, and let's try to keep it a bit short.
Hi, Laurent. I'll be quick. I think you alluded to this briefly in your previous slides about explainability for these models, especially because you need an explanation often for these really important decisions for network operators. So I have a question, but has your group looked into how to get around the black box nature of LLMs and these large language models, which are becoming increasingly complex? Thank you.
Not directly. I think we are still at the level where we are trying to understand what they are good at and bad at. That's kind of like the first step. Once we understand this, we can build system on top of them. And then we can start to think about how we can also, you know, like deal with hallucinations and explain what is going on. But on top of my head, I think you can do probably, I mean, with all these reasoning models, right? You have like, you see what they are doing and how they are, like what they are thinking. So there is a little bit of visibility, at least in the background process, that you can also kind of like reason about and show to the operators. You know, like they can also interrupt that process and they can put their own knowledge there. So I think my solution to that problem would probably be an hybrid human, you know, like human in the loop kind of approach, where, you know, like you would add like probably breaking points where the human would look in the middle of the reasoning. Does that make any sense? You know, and if not, then you would ask to backtrack. But this, I mean, to be honest, we haven't like looked at yet. Perhaps because these models are not yet really into use for that purpose. But they probably will be very soon, I'm sure.
Yeah, thank you. That's an interesting answer.
Yeah, thanks.
Okay, let's thank Laurent one more time. So our next speaker is going to be Sasan Elazar. So Sasan is a third-year PhD student at the University of Oxford. And she's part of the Computing Infrastructure Research Group working on sustainable networking. And she's also close to finishing her PhD and is currently on the job market. So if you're interested, let's speak to her after the talk. Yeah.
Thank you. So hello everyone, I'm Sausan Zahir, and today we'll present to you our work on carbon intelligent content scheduling in CDNs. And this is a joint work with William Nathan and Noah Zilberman from Oxford University. So content delivery networks are a distributed system of caches that serve users closely instead of being served from a distant origin site. And a major type of content that is delivered through CDNs is video. And video traffic is 65% of all downstreaming traffic on the internet, which is really significant. And moving this content from origin to servers or to users even have a very high carbon cost. And the question in this work is, can we make this content delivery greener without impacting quality? So caches are distributed everywhere in the world, and there is an opportunity to take benefit of the difference in carbon intensity between regions. So the carbon intensity is the measure of how much green is the energy per region or per country. And we have both the space and time granularities for this metric and to take benefit of. So to define the scope of this work, CDNs have two phases. We have the filling content phase from origin to caches, and then we have the serving content from caches to users. And in this work, we focus on filling content phase, specifically when we have pre-positioning of content. For example, Netflix pre-positions all of its content to caches ahead of time, and this means that it involves scheduling of this transmission. And we use Netflix here as a use case in the study. So traditionally, content fill happens during off-peak hours, like to reduce the traffic during peak and also to reduce the read and write to caches. So for example, we can have the content fill at 2 a.m. from origin to cache 1 and from origin to cache 2. But the idea in this work is that off-peak hours are an interval of time. It's not just one specific hour, and it could be better like to see some time slots where the carbon intensity is lower at both ends of this transmission. So it could be better to send the traffic from origin to cache 1 at 12 p.m. and then from origin to cache 2 at 4 a.m. So adding this carbon awareness into the content fill will help us reduce carbon emissions. And this is what we call carbon aware scheduling. Moreover, we can allow some multi-hop transmission, so from origin to cache 1 and then from cache 1 to cache 2, only if cache 1 and cache 2 share the same content. And this multi-hop transmission will also allow us to have further carbon savings. And this is what we call carbon intelligent scheduling. So this behavior is somehow similar to the delay tolerant networks, where we send once and then we wait for a better time slot with a lower carbon intensity, and then we send to the other site or cache. So to evaluate these approaches, we collected an open source data set from of Netflix use case. It's all open source. So we collected the Netflix peering points, like you see in the figure. We also have the top 10 list during 2023. So we use the Netflix top 10 list to estimate the new content that should be delivered every week. So we have per title the number of cumulative weeks in top 10. So if a title is new everywhere in the world, it means that this is a new content. And the average content distributed weekly is 3.5 terabytes. And this is to be distributed to every cache. So we multiply this amount by the number of sites worldwide. We also collected the power values of Netflix appliances that is available online. And for carbon intensity, we collected this from electricity maps. And all of this data set is for all the weeks during 2023. So what we did is we tested the 3 cases of the naive scheduling, like everything is at 2 a.m., the single hop and the multi-hop scheduling. The multi-hop scheduling was formulated as a mixed integer linear programming model. And we also tested different time windows for the content distribution, which means if we send only 1 day ahead, or it's not sending, it's planning 1 day ahead, or if we plan 3 days ahead. And obviously, if we increase the time window, it means that we are adding more time slots, and we obviously have more carbon savings. So moving on to some results, the single hop scheduling resulted in 13 to 17% carbon savings, whereas the multi-hop scheduling resulted in 53 to 64 carbon savings, which is much higher. And this is without violating the off-peak hours constraint, without changes to infrastructure. And we also noticed that the savings in Europe are somehow higher than the savings in the US. And this could be because Europe has more regions with green energy. Another aspect was to look at the scheduling window. So do we want to plan only 1 day ahead, 3 days ahead, 7 days ahead, because we have the weekly content. And we've seen that, well, obviously, if we increase the time window, we will have more savings, but we've seen that the maximum savings are up to 3 days ahead. But then after that, the savings will be less significant, or the increase in savings is less significant. So this is an example of a sample week for the US sites. And if we plan 1 day ahead, we have 36% carbon savings. If we plan 3 days ahead, we have 48, and then the remaining is only up to 52, which is not so significant. So maybe planning at least 3 days ahead will give most of the carbon savings. Some other lessons learned from this work are, first, these carbon savings happen with the same energy consumption. It's not like we have carbon savings and we are spending more energy, or we are having both carbon and energy savings. It's just only carbon savings, or because of the difference in carbon intensity, it's the same energy consumption. The second lesson is, well, this algorithm is applicable to many pre-positioned content delivery workloads, especially when we can plan at least 1 day ahead. So examples are video on demand, like in this use case. We have software updates, game releases, and so on. And finally, we also tested the idea of, well, let's not have a weekly schedule that changes every week. What if we want to have a static schedule for the whole month or for the whole year? Is this bad? And we checked that, and well, a fixed annual schedule can still give 39 to 47% carbon savings. It's like 10% less than the weekly schedule, but this is also a valid point if we want to reduce the amount of recomputations. So in summary, we proposed a carbon intelligent content scheduling algorithm for CDNs. We demonstrated it on the Netflix CDN dataset, and we've seen up to 64% reductions in carbon emissions. And this is all without violating the traffic constraints or modifying the infrastructure. We have some ongoing work on the different phases, which are like from caches to users, and also on the cache placement optimization. A final note is the code is available on GitHub, and I'm happy to take your questions. Thank you.
Any questions? So I have a question while people are thinking. Is there any particular reason you focused on CDNs specifically?
Yeah, so we have some other works for data centers, but for CDNs, what's important is the content and the pre-positioning that is mostly like for a larger time window. So this gives more opportunities rather than just job scheduling that is so fast for data centers and so on.
I see. Thank you.
Yeah.
Okay, John.
Yeah, I'm John Libby. This is interesting work, but I'm a little confused one level down, because my understanding is that like the energy usage of internet traffic is basically you add up all the routers and stuff and you divide by the amount of traffic. And so if you move, I can see that if you move the traffic to a different time of day, you would be dividing the power used, overnight or whatever it is, by the power used during the day. But unless you could actually figure out how to turn the routers off, I'm not sure, or unless you believe that this would allow the total amount of traffic to be lower, so you could just turn the routers off permanently. I don't see how moving stuff from time to time would actually turn into actual energy savings. Am I missing something?
Okay, so first, this traffic is the prepositioned to the content. It's not the content from the caches to users. So the caches to users, you cannot change the traffic, but from the origin to the caches, the one that you do during off-peak hours and so on, this is what we are talking about here.
Yeah.
And for the difference between the carbon intensity, for example, in this figure that you see here, what's interesting is that, well, content, instead of being coming from the US to each and other cache, you see that content will come to Sweden, for example, and then from Sweden to France to other places. So you will see some nodes that will act on behalf of the origin. But for example, because Sweden and France are greener than other places, so you will have a greener origin that will act on behalf of the initial one that is in the US.
Okay. Okay.
I can ask one more question. So you focused on the transfer here. So how is it related to the energy and carbon of the other aspects? Because you now have to store the data longer or in more places, or different aspects of the system as a whole. Can you comment on how it relates?
So the main thing is these caches will have the same content, so they will be getting the content anyway. So if you just change the, like you have the multi-hop thing, it's just instead of having it from origin to caches, it will be from origin to cache 1 to cache 2, because cache 1 will also have this content. It's not like you're adding it to cache 1. It will happen anyway. That's why the energy is the same. Okay.
Okay.
First of all, I think that the cost of moving data to the caches is not as significant as serving the client. So I'm not sure how significant this is. But if you try to optimize this, for example, you didn't look at the cost of transmission, how many routers you're going through, what is the route. Maybe you're going to a greener place, Sweden, but on the way you pay by moving through routers that are in places where electricity is actually expensive. So you might not have saved so much as you think.
Yeah, so for the carbon model or the energy model, for caches we have, like for any equipment, you will have the idle and the dynamic part that changes with the traffic. And for caches, you will see better proportionality. But for the network, the idle will be really, really high. That's why if you change the traffic on the router, it's not that significant. So that's why we focused on the caches here in this work. And the network is less significant than the caches.
Okay, let's thank the speaker again. So our next speaker is going to be Felipe Ribeiro Rosa. He's a master's student from Karlstad University, and he's interested in media transport and video streaming, and he'll be talking about end-to-end 360 video streaming over HTTP3. And he's remote, okay. Let's see. Okay, I see him. Okay, go ahead, Felipe.
Okay, thank you. My name is Felipe Ribeiro Rosa. I will be talking about end-to-end 360 video streaming over HTTP3 architecture implementation. I work with my professor at Federal University of São Paulo, Bruno Kimura, and wrote in collaboration with Simone Ferdinand and Anna Brucken from Karlstad University. First, the motivation for this work was on-demand video. It accounts for about 70% of the internet data traffic, according to this 2021 research. But the immersive videos, the 360 video, are relatively unexplored compared to the regular videos. And immersive videos, they have some difference. They have a constant interaction between the user, the client, and the server because you move your head. We kind of need multi-stream for the case we are working here. So in this work, we created an evaluation environment for those videos, and we tested some solutions. Here we have some difference between the regular and 360 immersive videos. We have in 360 videos, we have only the scenes partially visible, the viewport dynamic, we are changing directions. Some of the lower resolutions aren't really viable. And we have the videos divided into segments and tiles. Well, what are those tiles? Well, here we have an example of some person with a head-mounted display. As it moves his head, we want to look at different parts of the screen, and we segment the screen. We fragment the screen into little rectangles called tiles, so we can only download what the person is looking at. Because, well, not everything is visible, so this will reduce considerably the download size. Well, this image, I'm sure many of you have seen this over and over again, but just to show what we're working with in the transport layer, we have HTTP1 with TCP, then we have 2, we got head offline blocking, then we go to HTTP3, we don't have head offline blocking, we use quick instead of TCP, and combining those two things with the application and the transport, we have this system right here. So we have the head-mounted display. As it moves, you're gonna inform the application what are the visible tiles, so the buffer knows if they are present and can play the video, and the player can also predict which ones will be needed in the future, so can anticipate the request. Well, then the adaptive bitrate will select the quality, request the tiles and segments, download and put in the buffer. In the transport layer, we are using MP-Quick. We have both single and multipath, and we're also using the ACM, which is a modified version of MP-Quick, which we can use priorities on the streams. Well, this architecture, we have some operating modes. On the playback, we have blocking, which requires every tile which is being at the display to be downloaded, and non-blocking, so we exclude the upper and lower lines of tiles, which are usually only partially visible. Request, we have the default MP quick and quick, and we have using priorities, which are SACF. The different streams can be assigned different priorities. We have 255 different priorities, so we can have some objects downloaded first. The transmission is single and multipath. Single string sequential transmissions are supported in the architecture, but they are not the object we are evaluating here. Well, about the ABR, we are using Gelato. It's quite recent. It's a state-of-the-art adaptive bitrate. It's a deep reinforcement learned base. It has two pre-trained models we use, the random and plume static. Random had a random trace selection during training, and plume static, we have some strategy to mitigate distribution bias. The input data for training was collected from the buffer platform, and to use it in this scenario, we have some adaptations. So now it's client side. The download size is estimated because we don't have the segments download size, so we need to get the average of the tiles and see how many tiles we are looking at the time. And to quantify the stalls, we also include the tile miss event, which is when we need a tile for the playback, but we don't have. This is accounted as a stall for the ABR purpose. Now combining every approach, we have this multipath and single path blocking and non-blocking, and multipath with ACICF with blocking, non-blocking, and another strategy which is bitrate reduction. So the upper and lower line of tiles. Not only we have a lower priority, we also have a lower bitrate, so reduce further the amount of downloads needed. Well, the network emulation we did with MP Shell, a modified version of Mahi. We collected the traces from a Puffer TV from October 22 to October 23, same to use to validate Gelato. Classified those traces into 3 different groups, low, medium, and high throughput base. And when testing, we had some scenarios. Multipath, we put a high and medium throughput in each one of those paths to have an heterogeneous network environment. In single path, we only use high throughput. And we did this to isolate the impact of single and multipath transmission. Here's how we process the video. So we take the original MP4, have the initial encoder transform it to UV files. Then we have the tiling, which changes the encoding from 264 to 265. Then we need to take the tiled video and put it back as an MP4. In that stage, we collect the SSIM, which is a quality metric. Then we have the segmentation to create the final M4S files and MPD file. Well, here's the evaluation. We have first quality of experience. So this is rebufferation and SSIM, which is a quality metric. We have the top left being better. In both of them, the combination of every solution had the best results, both in Gelato Plume Static and Gelato Random. And single path had the worst results overall. Well, looking now at the rebufferation and tile miss, we have again combining all of the solutions the best results, and the blocking was worse both for multipath and multipath ACF. Now for quality of service here, Gelato Random had a better overall over Gelato Plume Static. Again, we have here we had the combination of our solution have a better throughput in the Plume Static, but in Gelato Random they all had a much higher throughput, and the multipath regular without no use of further things had the best throughput overall. For the download time, Gelato Random again, lower download time with the combination of all the solutions at Random have a good result, but at Plume Static they had a very high download time. Well, conclusion, we have implemented this architecture for with some state-of-the-art solutions. We have quality of experience improvements using multipath, and quality of service improvements with the multi-stream prioritization used. The stalls remain a big problem and a biggest challenge. If we look at how much stalls we had, it's not really applicable in a real scenario. And for future work, we are changing some things. We're doing a tile hit-based priority. So instead of just looking at the position of the tile, we are looking at when it will be needed according to the prediction to assign its priority. And we are planning to have some new components like tile level, ABR, not a segment level, and a real movement prediction instead of using a data set like we are doing right now. And thank you very much.
Okay, we have time for a couple of questions.
Hello, Amir Kulevin from Ericsson. Thank you for this work. Very interesting. I'm interested in like the scheduling problem here. I think you probably just chose to always have one stream on one path, right? Or did you also try other approaches? And did you have multiple streams on one path, or was it always like one path per stream?
Well, so we have one-to-one string and tile mapping. So we have lots of streams from each path, but we are planning to change that. Some other modifications we did in this meanwhile show that one-to-one mapping sometimes not good because you can have too many streams at the same time depending on the situation. So yeah, we are looking into that.
Okay, looking forward to more results. Thanks.
Okay, Sergey.
Yes, Sergey Gorinsky again from MD Networks Institute. Thank you, Felipe, for the work. So immersive streaming has been kind of the future for a long time, right? So we're still watching, I know, everything in 2D. So what's your perspective? Maybe it's going beyond the specific focus of your talk, but is it necessarily web transport or some other aspects which prevent it from all of us sitting here with HMDs and participating in this conference in 3D?
What? Sorry, take the
Okay,
part.
so the question, what are you think the key limitations for the adoption of these 3D immersive streaming? You know, is it really networking or transport issues that prevent it for wide adoption, or it's something else?
Well, I think it's some network issues. As I said, some of the lower resolutions are not really viable because of the tiling. So the download size sometimes can be very big. So it's constantly stalling. So we have some network limitations which is need to mitigate with application solutions combined with networks. So, but I think with where the network is heading, it's gonna have a wider adoption in the future. It's a better, for instance, 6G. We are also researching that really fast. I think that's gonna be a breakthrough for immersive videos.
Okay, well, just to push back on this a little bit, because even now we're watching regular videos, let's say over YouTube, you still get sometimes stalls, so you don't have a perfect experience as well, right? You still have, I know, sometimes very low resolution, but people still do it massively and everywhere. So I'm just asking, maybe just because something have to do with other aspects, like maybe head-mounted displays are too bulky, inconvenient, or something else that prevents this type of streaming from exploding and becoming the mainstream, apart from video gaming.
Yeah, we also have this problem. Well, about head-mounted display, you have the cardboard with a cheaper option, so we can turn your cell phone into a head-mounted display. So I don't know if a hardware impediment is something that's really locking it, but when it comes to the installing or not a perfect experience problems, when we talk about those immersive videos, not having a perfect experience can be a lot worse since it's right onto our face. We can have a nausea, for example, and other problems. This is go back to the also hardware. So sometimes the cardboard, your cell phone is too small. You can have a good experience in, unlike some the 2D videos where it's a small screen, but you still you're not gonna vomit from not having a good experience.
Thank you.
Okay, thanks to Felipe. With that, I guess we'll go to the break. So it's a 30-minute break, and then we'll reconvene at 11:30. Thanks, everyone.
Yeah, it was removed.